Okay. Okay. Thanks everyone who joined. My name is Tal. I'm a senior director for cloud native security research at Contrast Security, and I'm going to talk to you about serverless security. Just a few words about why me, or who am I, what am I doing. Why me? Let's start with that. I started last year, I started a company in Israel called Cloud Essence. We are doing cloud security testing for serverless applications. We got acquired by Contrast last year. And previous to that, I was heading the research at Protego Labs and other serverless security in protection that was acquired by Checkpoint a year before. In general, you can reach me through social media on GitHub, Twitter, or my personal links. I'm also teaching cybersecurity in Quinnipiac University, a Connecticut-based university in the United States, which has a master's full online program. So if you're interested, shoot me an email. Okay, so why is serverless that important? We'll get to serverless specific soon, but cloud native in general, serverless is part of cloud native. Cloud native in general is presumed to be the future of application development. IDC predicts that this year, by end of the year, 70% of all newly deployed enterprise application will be deployed as cloud native. That is based on architecture, which is hyper agile, which uses containers, microservices, and serverless functions. In general, we already see a massive transformation into cloud native. We can find at the top iRobot, Skyscanner, Netflix are companies that already utilize everything, almost everything, as a cloud native environment. And we can see some big companies, not only startups like Capital One, Walt Disney, eBay, Coca-Cola, etc., that are moving there, and they are still working in some kind of a hybrid solution. Some of their applications are cloud native and some are monolith. But cloud native, what does it mean? It's not just a development pattern. It's not just using containers and serverless. It's a completely different architecture. So we don't have one big flow that's what we are used to know from the monolith, from the traditional application. Everything is deployed into one big logic. Instead, what we do is we utilize microservices or nanoservices, which basically tear everything apart to small pieces, and then a lot of work in connecting them together into one flow. So it's a combination of code and your infrastructure that together builds the cloud native application. The cycles are also different. It's not a water flow life cycle, which you build, test, and continue with the flow, but instead it's more of a DevOps or DevSecOps. Now it's also called operation, where you work in a hyper agile environment, and every cycle is in short cycles, and you keep going with them. So the process is different, is less manual. You don't have, hey, today we're updating the environment, so let's have a full server update or downtime. Instead, the process is almost completely automated, and the decision is also taken by the developer themselves, which takes care or owns the security and the code into production. It's not managed by high hierarchy as before. Serverless architecture, in general, it's like a big puzzle. It's a lot of resources, could be hundreds in some applications that we saw, it's even thousands of resources that each is connected to another using some kind of a glue of our infrastructure or a configuration. And all of that together becomes one big application. But if we're talking about security here, so we need to understand that these resources or services, in many cases, they are stateless, or they don't really understand the entire flow, but they own only the specific small piece of logic, which means that in many cases, we will have to apply security to each one of them separately. So it has a lot of security challenges, and we will discuss that. Okay, when I talk about serverless, what do I mean? We'll discuss some of the biggest cloud providers, but in general, serverless means that you don't own the server where you run your application. So the server is given, we'll talk about it in a second, is given by the cloud provider, AWS, GCP, Azure, etc. And when the code of a serverless function, for example, needs to run, basically the cloud provider spins up on demand a container, runs the code, executes the codes, and then shuts it down. The triggers for these type of executions are based on cloud events. Cloud events it's an event-driven architecture. Cloud events means that something happened in the cloud. It could be an API like we're most familiar with, but it could also be someone uploaded a file to a cloud storage somewhere, or someone sent an email to someone, or logs that arrived and collected, or analytics. And all of that is configured to allow the serverless function to run. The environments are usually read-only, so you cannot really change anything in the environment. In the container that runs the code, it's a read-only environment. In AWS, you have the /temp directory, so you can write the data there, but all the environment itself is a read-only. Other cloud providers have a little bit different, and we'll talk about that. The code or the environment terminates when the code finishes the execution. So once the code is completed, the container itself shuts down, so you don't really have access to it. You cannot SSH to the environment, to the runtime environment of the function. It just executes the code. So when it spins up, it has the code already inside. The data is also temporary. So when the container shuts down or the execution is completed, the data that was inside is deleted or just eliminated. And we have an asterisk there because in order to maintain performance, the cloud providers really just put those containers aside and reuse them. So in some cases, even though it's not controlled by us, one execution can have data from previous execution. But again, we cannot rely on that or know that it's random from our side. The code, as I mentioned, reside already inside the environment when we create the functions. Also, the keys for the function in order to be able to interact with other services is also inside the environment. So when the environment spins up, the keys are already in there. So when you need to grab data from the database, you have already access to that. And we'll talk about that from a security perspective. All right, so I mentioned an event-driven architecture. What does it actually mean? It means that something happened in the cloud. So API, S3 bucket, DynamoDB, IoT rule, etc. That executes the code. This is what we own. This is our code. It executes our code, which usually processes some data and interacts with other services. And there are many services that we can interact with, and the security risks really mostly reside here. All right, so let's understand what is this single purpose container better. So we have AWS, Azure, and GCP, and there are many others, but of course we cannot cover everyone. Those usually have the most, the highest part of the market share. Ephemeral. So as I mentioned, AWS really just eliminates the container after it runs, so it doesn't leave anymore. On Azure and GCP, it resides a little more, depends on the configuration. AWS has the read-only environment other than /temp. On GCP, you have the /temp and /home. In Azure, it really just continues to live. Again, you can change that configuration. Different triggers. AWS is, of course, behind, in front of everyone with, I think today is already almost 30 different triggers. So email, code, SNS, SQS, so queues, authentication, third parties, etc. Azure and GCP are a little bit behind. The source code is located under /var/task. You can also find it in this folder. In AWS, as we know from previous monolith application, is www.root, and GCP had a user_code folder which holds the source code. Okay, so what are the challenges there? So when you do some things in a small scale, it doesn't really problem. You can investigate, you can put your efforts into it, you can have security teams looking at it. But when you need to scale, that's a little bit different, because if developers shift new or create new functions on a daily basis, or at least change them on a daily basis, the security teams cannot really keep up. So you have a lot of services on AWS. You have almost 200 different services, frequent deployments. I know organizations with hundreds of deployments to productions in a week. That because you don't really need to wait for the entire server to update the server, but instead developers push new small functions or changes into functions which run separate into production. So think about how hard is it for security teams to follow. Who is talking to who, or exactly what is talking to what. As we've seen before, with a complex puzzle there, that the security teams really don't know what's going on in the environment. Yeah, they know if there is an API that is exposed through the web, the front end, through the web application, but in many cases, it's just back-end code that runs based on other types of events which are not exposed to the world, and security teams have no idea what's going on. This is from experience. Many developers, small security teams, we know that in the best organization, you'll have one security person for each 10 developers. This is for mature organizations. So it's hard for the security teams to follow. How do you know what's important? That's tricky questions. You don't always know what's important unless you really talk to the engineering. In this case, you'll also have to talk to the DevOps or to the infra teams to understand really what is going on. And maybe the biggest question that we have is the security even the same if we're approaching now a security assessment for serverless application? Does my previous expertise enough, or are they enough for understanding the security challenges here? And as I mentioned, part of the application is the infrastructure, is the cloud. So if we have a cloud infrastructure team, a DevOps team, an engineering team, and I have a security issue in the cloud or in the application, who takes care of it? Is it infra? Is it engineering? Who should I talk to? Okay, let's try to understand what is the state of security in general. So recent checks that I did was showing that, serverless is keep rising. Of course, this is quite old, but if you look, it will continue to grow as expected, but the security really remains the same. No one is actually no one, but there are not enough information or people that are checking specific security for serverless. You can see it jumps between 2 in the best cases to 1, and I'm pretty sure this one is me. From that period on, I'm sure there are, it can reach 2 or 3, but not more than that. So we talked about, is security the same? So can we use the same AppSec, application security, to our serverless application? Does it apply? Let's understand some of the risks that we have in serverless applications. So this is an example of a function, a Lambda function, and AWS Lambda function is their serverless compute. So small lines of code. Usually, really, the function doesn't do much here, but you can see here that it communicates with an orders table, and the put item here is basically the API call that makes write into the database. So what happens is that developer needs to give this function the permission, the IAM policy for the function to interact with other services. Usually, the developers, as we know, they will do something as quick as possible for it to work. They will look into documentations and they will see what they need to do in order to make it work. So if we look in the documentation or in Stack Overflow or things like this, what we'll find is that we need to assign DynamoDB access with a wildcard, because the wildcard means that this function can do any operation. So that would work. Of course, when I'm saying that this is what developers will do, it's not every developer. Of course, we know that there are developers or organizations that take care of security or IAM in a different manner, but we'll talk about the problem at scale. So the developer will assign a DynamoDB wildcard policy here to any resource on the account ID, any table, basically. That's what happens with this is that if this function is then identified as vulnerable, someone who has access to this function can execute any activity, any action on any table in the cloud account. So it's not just the application, it's not just the database, but basically it's any operation in the cloud account. It can be deleting tables, modifying tables, creating tables, different, even if they are not related to that specific application. Okay. So as I said, the wildcard is bad because it's a bad practice, because that gives the function a lot of permissions, which it doesn't really need. So what do we need to put here? What we would need to do is to convert the put item here to the put item action in the AWS IAM service, and then put the table name here. So in that case, what will happen is that the function will only have access to write a single line each time its execution to this specific table. Think about this as a granularity that you would not be able to achieve in a monolith application, because this really takes just the write action to the database, just the activity of writing into the database, and limits the attack surface here, or the permission, the access level, to just this active action. So if you take a monolith application, like a traditional application, and you have thousands or millions lines of code, and you could say, no, but inside this code, this function, this part of the code can only have permission to write to the database, and this part will only be able to read. This would have been great, but it's not possible in monolith application. In serverless, it does. So it has a big opportunity here, but the problem is when we try to scale things, because if we have one function with 20 lines of code, then it's easy to understand what's the security or what we need to put here. But if we have new code written every day, and hundreds or thousands or tens of thousands, and I know organization with millions, then it's going to be hard to do it manually. So you'll have to have some automated process there. But how would you know if it's in the code? Another challenge that we have is the loss of perimeter. If before we had one way in, well, usually HTTP or some kind of a gateway or a load balancer, but we always had one way in. What we would do is put all our security tools in front of it. So we'll have DLPs and firewalls and gateways and configuration, everything in there. But when we think about serverless application, really we lose this perimeter. And what happens is that developers can have access, or users can have access, or users, or maybe the system could execute code from various different entry points. Could be analytics, could be direct APIs. You could be just calling the code. So I can actually use an API to execute the code without going through any network component. Could be static assets, uploads, downloads, or whatever, mobile or whatever that is. Okay, so let's understand how we gain access to resources in different environments. By that I mean I have a function that runs that how from the function itself I can gain access to different resources or services, so to the database, for example. So if we take GCP, inside the code we have a metadata service internal, so metadata.google.internal, where we can connect using the meta flavor header with the access token and get a bearer token. This bearer token, or JWT, can then translate to access. This token can then be used to access or retrieve data. So you can see here, I'm doing a call to this metadata service, I'm getting the token, and then I'm doing a curl, so a simple request to a specific storage on a specific project, and I'll get the data back. So if I have access to the runtime and I can run this command, I can get the token. If I can get the token, then from the internet. Now, this is from the internal service, but from the runtime of the function, but this can be from my own computer, and I can access the data. On Azure, something a little bit similar, we'll do an env print, and we'll see the endpoint and the secret, and then we can use a curl command to an internal service to get the token using the secret header with the secret that we got, and then we will get an access token. From that, using that access token, we can then connect to the Azure system or APIs from the internet and then get data. So again, if I'm running inside the function and I have access to the execution, to the runtime, I can run this command, get this data, run this command, get the token, and then from my own computer, and we'll see that in the demos in a few minutes, I can interact with other information. Sorry. The information that I can reach depends on the policy that is given to the function, as we discussed before. On AWS, it's a little bit similar. Running the env command will print the environment variables. I will get the session token, the access key, and the key ID. These are permanent. This is changing. And then using the AWS CLI or any API call that I want to make, I can call AWS Dynamodb list tables, get the list of tables using this token. Okay, so we talked about the security challenges, and we talked about how we get or how we connect to other services when we're in the runtime. Now let's try to understand how can I get into the runtime. I told you there is no SSH to the environment, so we cannot hope or do some network probing and try to understand maybe default credentials and log into the SSH terminal and then do that. No, we cannot. But the runtime execution, if there is a vulnerability inside the function or in the configuration, we can then try to execute commands in the runtime. So this is an example of a scenario that we'll show now. So there is a user interacting with a Slack chatbot. The chatbot communicates with the Slack API, of course, which is configured to go through an API gateway. The API gateway will execute the Lambda function, which will grab data from the database and will print it back to the user. So this is the Slack chat. There is a chatbot here that just replies back to different messages. There is a vulnerability inside the function. The way that I know it is because I explored a little bit before. This is a CVE. It's not like a specific vulnerability. It's CVE known using a specific dependency. And you can see here, I'm trying to run a command injection attack, require child process, and then run some commands. So I'm doing here a curl or an execution to curl to hacker.ngrok.io, which is an HTTP tunnel that I have here. And what I want to print is a test. Now that I figured out that it's vulnerable, this request is coming from the function itself. So now I can change the test to get some more interesting data, and I can do ls, for example, get the file inside the code, inside the runtime. Now that I know the file, I can try to read the file, right? So cat index.js, and I probably want to base64 it because we don't know what's inside. Maybe it's even binary. So I got the base64. Now I can go to the ngrok console, get the data that I received. It's basically a base64 conversion of text. I'll just copy that and decode it on my own computer. Then I got the source code of the function itself, and I can see the API calls to the Slack channel. So now I know that there are some keys here that allows me to communicate with the channel, and I can see a DynamoDB, so a database call here. So right now, using the code, using the code, I crafted a specific payload that I don't need to go through the terminal anymore. I can interact with Slack because the code can interact with Slack. So what I'm doing here is I'm creating a new Dynamodb client. This is just a syntax. So require AWS SDK allows me to create AWS API calls. I'm doing a scan. Scan reads the entire database, and the table name, as I saw here, is inside the environment variable DynamoDB table. I don't even need to know the name, the bot token, he's in the environment variable. I can just use it because it's in the runtime. And then I'm going to send it directly to the Slack channel here. And I got the entire database. This is because there is a vulnerability in the function, but also because the function has permission to scan or to read the entire database. If this function only writes to the database, I should have only allow it to write into the database in the policy. Not that it's going to prevent the attack, but it would limit the attack surface here. All right. So we saw one. The entry point was in a third-party application, but basically there is some kind of an API behind it. Now let's see something is a little bit different than API, which is a cloud storage. What happens here is I can upload files. The files are going to sit in an S3 bucket. Once the file is uploaded to the bucket is configured to execute a Lambda function, so some code, and the code. I'm uploading it through an API, a web API. the function gives me a token to upload directly to the bucket, and then the bucket interacts with or triggers the code. So let's see the demo, sorry. Okay, so what I'm using here is DVSA, a damn vulnerable serverless application. So it's a serverless, a vulnerable by design serverless application with hundreds or dozens of services and resources behind it. And there is a feedback channel here, which page here, which I can send messages and also add files. So if I want to attach a file, I'll just select the file. And I can see from the response, the request that I'm sending, uploading a file, and the response, I get a URL, which is a pre-signed URL to upload a file directly to the S3 bucket. I'm not actually going through the application, but I got from the application the assigned URL, and I'm using the assigned URL to upload to a cloud storage. But when I upload to the cloud storage, it executes a code that processes the file, and this Lambda function that executes that runs the code is vulnerable to command injection. So what I'm doing here is doing a command injection that calls, again, this HTTP channel. I'm doing the HTTP channel so I can get back the information because it doesn't come back in the response. Many serverless functions are not synchronous, so you don't have a request with a response data, but instead it's more, as I said, asynchronous, event-driven. So now that I have the file name set like this, what I'm doing is I'm printing the environment variables, which we saw before what they hold. So I'll run that. And you see, I got some requests here. And now that I have the data, the environment variable, I will decode it. And I get the tokens. As I said, if we copy the session token, the access key, and the secret key, we can basically run commands from our own computer to interact with the cloud services that are allowed by the function. So let's see how that happened. AWS CLI interacting with S3 service. Well, I'm using the profile defcon here. And now I got all the buckets or all the cloud storage. Now, because the function has permission to do more than that, I can continue to interact with the services and get more and more data. And you can see I got some receipts here, and I can even modify a receipt and upload it back to the cloud because the function has access to do so. So my tokens, my access keys, also have access to do that. So basically, I uploaded a file, and the case here would be that maybe I uploaded some file that I purchased something, and then I can call support and tell them nothing happened, nothing arrived, and they'll see the receipt. But anyway, this is just an example. Okay, let's continue. So how do we understand, or how do we find security vulnerabilities in a serverless environment? Can we use the same security tools that we used before to test for serverless application? We can, but it's not going to be as good as you think it would. Most of these tools are really ignorant to the environment, so they don't really understand anything else other than HTTP or some kind of an TCP-based interaction with the code. They have the request coming in, so the sink and the source, they follow, but they don't really understand things like interaction and configurations, which is cloud-based. So they don't have the context. If a function has access to, has a vulnerability, let's say, but it cannot do anything because the permission doesn't allow it, then even if there is a vulnerability, a potential vulnerability, it's not exploitable because the function cannot do it, and it is going to be blocked by the infrastructure itself. So they would produce a lot of false positives and a lot of false negatives because they cannot see anything that doesn't have a sink and a source or an HTTP usually. If something happens because there is an analytic service running in the background that and every part of data processing runs a function, then what happens is that when you run tests, they cannot test it. You can, if you're using a tool like a DAST service, for example, you cannot even point it to the endpoint because there are no endpoints in this case. So what would you do? Slow executions. It's not working as, hey, I have a new version of the server. Let's run a scan now to see that everything is in place. No new vulnerabilities. No, different lambdas are added to production on a daily basis. So it's hard to scan or to run some security testing for them. So basically that blocks the developers and disruptive to the CI/CD. So security teams, so developers and security teams don't really like using traditional tools. And if they do, it's because they have the licenses, but they don't really have the ability to get the best information. And it's hard to scale in such a big environment. What you should do is do something else. Because you have context of the cloud, you can actually identify automatically everything that happens. So if a developer creates a new API, connects it to a code, you can actually go through the entire process because these are all sitting in the same or sitting in the cloud. And if you have the right tools, you can actually monitor all of them and understand the flows and what's happening beside them. What we do at Contrast is that we test those scenarios with malicious payloads, and then we verify that each of the resources to see if they are vulnerable or not. And if they do, we know also what is the impact, what is the blast radius for the entire account. There is a talk that I gave in Black Hat about attacking serverless function using Alexa device, so with my voice. What I did was a SQL injection using just my voice. Of course, this is not something that you can run Dust on or even SAST because they don't know the source or the sink in this case. So this is a different approach that you should try to understand. Okay, so we saw some examples, but there are many more risks for serverless. I'm not saying that serverless is not secure. I'm just saying there are challenges and security risks which we should account for and we should understand first of all. So first of all is the event injection, which is basically running injection attacks through events, whether they are synchronous, asynchronous, direct or indirect. Authentication, we mentioned before. We need to make sure our entire system is going through authentication, zero trust maybe, even if their services and resources are stateless. Sensitive data exposure relies everywhere. Overprivileged function, we discussed that. Vulnerable dependencies, we all know, I don't need to add more about that. Insufficient logging and monitoring, so we don't have the ability, well, we have, but we need designated tools to be able to monitor and log cloud-based application or serverless application because the data resides in locations that we do not own in most cases or as services. So for example, in AWS, you have the CloudTrail and CloudWatch logs, which you should then monitor and get the information from. Open resources, so basically resources which are misconfigured to have access externally. Denial of service versus denial of wallet. Shared space, I mentioned before, Lambda functions or functions in general can have data from previous executions by mistake, and of course, secret management. You can read all of them in the OWASP Serverless Top 10 project. Right now, it's an interpretation of the original Top 10 into a serverless environment. We're working on creating a new serverless and tailored Top 10. You can participate if you work with serverless. So we would love to have your information participate in this open data call. Also, if you want to try it yourself, you can use the OWASP DVSA project. It's an open source project. You can install it and practice. There are videos, there are examples of how to use it, and you can try it yourself. Make sure when you do, if you do not install it in production, because it will deploy or production or any important AWS account with sensitive data, because it will deploy functions with a lot of permissions there, which are vulnerable. With this, I will conclude. Thank you very much to everyone who participated here. If you have questions, I'd love to answer in the remaining few minutes.
Thank you very much, Tal. That was interesting. I knew about the serverless, the dumb vulnerable serverless application, but I have to say I have never played with that. But yeah, like most of the stuff is like, you know, it seems like the wheel repeats itself with all the misconfigurations, and that's usually kind of the main issue with all of this. So I was wondering, like, if you could share like any type of story where there was an incident where the entry point was one of these serverless applications.
So the example that I gave was from an S3 bucket and basically an API gateway. Those mainly would be the most common ones, because they are many times they are configured or misconfigured to be open, but there are other services. I have some, or I saw some security vulnerabilities in services which would be a little bit harder to exploit, because they would not have an endpoint, so you cannot really reach them from the internet. They do have an endpoint, but it's an AWS endpoint, so you need to have the right access credentials to them. Maybe the most interesting one was using AWS pipelines and code commits. So when developers push new code, there is a process that spins a function behind that. Basically what it does, it takes the code, push it into a container, and runs some processes in the background to see tests and everything, to see that it's not or it's running and going through the end-to-end test or integration test. And in the function there was first of all the misconfiguration, like usual, especially because it was like a testing or a pipeline function, so it was not exposed to the internet, and they had paid less attention to security. So it had multiple permissions, over permissions in containers and EC2s to spin up, spin down, whatever containers, and it had a vulnerability that you could basically determine the location where the code will be downloaded to or will be sent to the container afterwards, because it would zip it in a way that you gave it and then push it into the container. And what happened is that you could change the code structure so it would override code in the container when it downloads it into the container. So if the developer or someone who has access to it, even that they don't really have direct access to run code on the container, they have to go through the pipeline. They could structure the code in a way that they could run their own code inside the container and do whatever they want. That was a very complex but very interesting scenario.
Cool. Thanks for sharing that. So we don't have any questions on the Q&A, and also we are out of time now. So thank you so much for your presentation. I appreciate the time that you took to be with us today.
Thank you very much.